So in the previous two tutorials, we worked with regression problems where we were predicting continuous values for given input values. But in this tutorial, we'll be working with classification tasks um, where we deal with categorical data. So in particular, in this tutorial, we'll be working on an image classification task where uh, we have a data set that contains multiple images, and these will be categorized to different classes. So we'll be working with a popular data set called the MNIST data set, which contains images of handwritten digits between 0 and 9. So we'll be designing a machine learning model that would train on a subset of these images, and then we'll also evaluate the performance on another set of images that it hasn't seen before. So these images are 28 cross 28 images, and they're grayscale images. So TensorFlow has this data set predefined. So we can just use the TensorFlow API to load it. And when we load it, we'll be splitting it into a training data set and a testing data set. So the reason we do this is that so that when we train our model on the training image data set, we want to ensure that it's not overfitting to the images that it sees, and it's able to generalize well. So we will be testing it on images that it hasn't seen before. And that's a good way to evaluate the performance of your model. So now that we've loaded our data set into training images, corresponding training labels, testing images, and corresponding testing labels, let's look at the shape of these NumPy arrays to get a better idea. So we see that totally there were 70,000 images in our MNIST data set, and you split them into 60 and 10. So we have 60,000 training images and we have 10,000 testing images. And the shapes are 28 cross 28 for each image. And the labels are essentially 1D vectors containing scalar values between 0 and 9. And these are your class labels. So let's visualize a few of these images. So if you use print, we see that each image is stored as a matrix of numbers. So a better way to visualize this would be to use the ImShow API from matplotlib. So here we see that the image is a 5 and the corresponding class is 5 as well. We can look at it for another example. And we see that this image is clearly a 0 and the class label is 0. So now, before we move on to designing our model, we'll be normalizing these images. And this is a good practice to scale them such that they, like all the pixel values, fall into a constant range. So here we are normalizing them to fall in the range between 0 and 1. So to do that, we'll be dividing the training images as well as the testing images by 255 because they're grayscale images and they range from 0 to 55, the pixel values. So now if we print a sample training image, we see that all the values are between 0 and 1 and they've been scaled. Okay, so now we have our data ready. Let's move on to designing our neural network. So in the previous regression examples, we saw that we fed either a single x value or x1 and x2 to a set of neurons in the input values. Here, we'll be working with images which are essentially 2D tensors. So before we feed them into our neural network, we will flatten them out to form a 1D tensor, where each pixel will then be fed into every other neuron. So here we're dealing with 28 cross 28 images. We'll flatten them out to get a 1D tensor of 784 pixel values. And then each of these 784 pixel values will be fed into all the neurons in the first layer. So we see here that we are taking an example neural network where the first layer or the input layer has 20 neurons. And then we have the output layer, which has 10 neurons. So it is important to have your output layer with 10 neurons because it reflects the number of classes that you'll be dealing with. So here we deal with 10 classes, so labels from 0 to 9. So we have 10 neurons in our output layer. So yeah, so given that, now let's define our model. We'll be using the sequential API as well. So we'll be first defining our flatten layer, which takes inputs of shape 28 cross 28, and then it will flatten it into a 1D tensor of 784 elements. Given that, then we have our hidden layer, which has 20 units or 20 neurons. And then we have our output layer with 10 neurons or 10 units. Activation functions here are used to manipulate outputs of neurons and also introduce some form of non-linearity to enable the model to learn more complex relationships between data. So now that we've defined our model, let's go ahead and define our optimizer and loss function. So we'll be using an Adam optimizer. And loss function, notice that instead of an MSE loss, which is the loss that you would use for regression tasks, we'll be using a cross entropy loss. And this loss basically deals with differences in probability distributions. So in this model, the 10 output neurons will output a probability distribution across all 10 classes. So what happens is, so if you have 10 classes, it will all output values such that if you sum them up, they add up to 1. So the neuron or the class that has the maximum value of probability, that would be assigned. That is the class that would be assigned to the input image. And that's what softmax activation function does here. It converts the output values from the previous layer into a probability distribution. So, and cross entropy loss works on different distributions and measures the similarity between distributions. Next, now that we've defined our model and we've defined our optimizer and loss function, we'll go ahead and train our model using model.fit. We'll be fitting it on our training images and training labels, which are our ground truth X's and ground truth Y's. We'll be training it for 20 epochs. And also we'll be feeding it the validation data, where effectively what happens is that every step of backpropagation, it would also train that model on this held out data to see if at every stage it is actually performing well on data it hasn't seen before. So the main difference is that there will be backpropagation and there will be weight updates using the training data, but validation data is just to test it out and see whether it's working all right. But there is no learning from the validation. So we will be running this model. As you can see, this model is slower compared to the regression models we worked with, mainly because now we have, as opposed to 1 or 2 input values, we have 1 or 2 dimensional input values. Here we have 784 dimensions to our input. And we also have 60,000 input images. So that's the reason it's taking longer. And after we train, we should be able to see good accuracies for our training as well as validation data set and small losses. So this seems to be pretty good accuracies of 97% on our training data set and around 95% on our validation data set. So now we're done training, let's evaluate our model. So ideally, you would have different validation data sets and different test data sets, but in this case, we are using them as the same thing. So we use this API called model.evaluate that will essentially run the model, the learned model or the trained model on new validation images. It would output, it would then calculate your predicted labels, and then it will compare the predicted labels with our validation or our ground truth test labels. And then it will return an accuracy. So it returns an accuracy of about 95%, which is also really good, and also a loss of only 0.15. So we can say that our data set, or sorry, our model is performing pretty well. Now from here, we are only able to sort of see how well our model is doing in terms of accuracy and loss. But we could use the model.predict API to sort of visualize and see what our model is outputting for every validation or testing. So let's run model.predict on our validation images, and it will return an array or a 2D vector called classification. Now, the shape of classifications would be 10,000 cross 10, because for every image out of the 10,000 images in your test data set, it will return a probability distribution across all 10 classes. So let's run this to understand better. So for the first image in our test data set, our model returns this array, which is essentially 10 values of probabilities across each of the 10 classes. And we see that they're all pretty small values, but this value seems to be the largest. And this is at index 7. So the model will predict class 7 for this particular image. So we're using an np.argmax to reflect that. And you see that our predicted class is 7. And then when we print out the actual class, which is the ground truth labels, that was also 7. So we can say that our model is doing well. So this is just visualizing our model. So what does model.predict do? It returns the probability distribution across all classes for all the images in your test data set. So in this section, it's the exact same steps that we performed before, but we're just explicitly defining our layers as layer 1 and layer 2. This is only because this gives us a way to use the get weights API to inspect the weights and the biases that our model has learned. So we just let this run. So in this section, instead of inspecting the actual values of the weights and biases, we will in more detail look at the number of weights and number of biases that are learned. And we will see why that is so. So a good thing to remember here is that the weights are associated with connections, whereas the biases are associated with the neurons. So now that we have, say, 784 pixels here, and we have 20 neurons, we would have 784 into 20 connections between the inputs and the first layer of the neural network. So that would be the same number of weights that are learned. That would be equal to the weights that are learned. So let's go ahead and see that. So these are just the weights. But the more important detail to learn or to observe is that we have 15,680 weights in our first layer. And that is coming from 784 into 20. So we have that many weights because weights are associated with each connection. So that explains why we have 15,680 weights. And if you look at the number of biases for layer 1, we get 20 because they're associated with all the 20 neurons in layer 1. Now, if we go to layer 2 and we see the number of weights, we get 200. Now, this is because if you look at our neural network diagram, we have 20 neurons in our hidden layer and we have 10 neurons in our output layer. So we have 20 into 10, 200 connections, and hence we have 200 weight values. And then when we run the number of biases for the second layer, we get 10, which basically are associated to the 10 output neurons in our output layer. And so we see that weights are associated with connections between the neurons in the previous layer and the next layer, and weights and biases are associated with the number of neurons in that layer.